Right, hello everyone. I'm just, as always, checking if all the streams are running. Stream is still considering that we are connecting. Last time I had to wait for a while before the connection actually considered that it is actually connected. Yeah, so YouTube thinks it's connected, and there are 4 people. Hello, everyone. And Twitch probably will catch up soon, too. All right, so... hey! We worked recently on the FX2Grok and the logic analyzer for with FX2 Today we will be starting a new project, but before we do that and start working on something new, let me just give you a few updates on the status of FX2Grok, just to clean it up. So I did some schematic cleanup. I made some 3D models. I ordered the boards from Oshpark. And ordered some FX2s from China, because unfortunately DigiKey sells them for some extortionary prices for some reason. It's like, I don't know, this economy works weird. And then I also ordered some samples from Samtec for cables and connectors. They didn't confirm those samples yet. But I assume they will confirm it next week, because I think I did it on Thursday or something, so they might not have gotten to it. Then I'm working also on figuring out some alternative cables, because Samtec is not the cheapest solution. And so and that's something I'm working on. And one person on Twitter asked if there will be a edited version, because they were overwhelmed by the 9 hours of work that we put here on the stream. So yeah, I will be making some smaller edited versions, hopefully. And we will see how that works out. As always, and thank you for everyone who commented and watched the video. It's very much appreciated. It's community work, this whole project. Yeah, so let me show you really quick what the FX2 status is on the schematic. So let's go to the desktop. Yay, Inception. So as you see, I went through the schematic and I created blocks for different sections of the system, added some legends, cleaned it up so that it is fits together and it is nice squares. That's how I like having my schematics, so that they're pretty clear what belongs to what. KiCad does have support for nested schematics, so if this stuff doesn't fit on one sheet, at some point you start recursing it into subsheets, but fortunately that was not necessary here. We could just document it in blocks like this. That was one part. Then the second thing was a little bit more work on the board, and I did that off stream because this was relatively boring, and I was just watching Micah's stream while that was while I was working on that. So I thought people might be there anyway, so no need to try to compete with that. Anyways, I think it was great, and I did this boring stuff off stream. What it resulted in, I was able to squeeze out another, I think, 2 millimeters in length of the board, which like funny side fact. It's and now only 1 millimeter wider than the BitMagic probe. So let me show you how small that thing is. If I go onto the camera here so that I see. Focus. There you go. That's BitMagic probe. So the new logic analyzer will be this plus 1 millimeter wider. So I think that will be a fun small device. So it will fit in your pocket or in your travel kit very nicely, and you can use it for different projects. So yeah, one more thing, just it's a fun thing I like doing to show how things look. Oh, what happened? So the model for the 3D model for the QFN disappeared. So yeah, I think I know what happened. That was in the next step. I redid the footprint. So there is no correct QFN model for this footprint. So what I did is actually reuse a different QFN model, and someone even on Twitter mentioned your pins don't match, and I'm like, yes, they don't, because I was lazy and I didn't create the proper model for it. There is a script in KiCad to generate models. I mean, an external script that you can create different parameters for models, and I didn't go down the rabbit hole of downloading that and figuring out how to generate 3D models with it. So I was just lazy. I will eventually figure it out. The other interesting trouble that I ran into was getting this 3D model of the Samtec connector. So if you ever download Samtec models, just don't bother with the VRML models that theoretically would be read directly into KiCad. They just don't work. Whatever Samtec is exporting, KiCad is not happy with, and not even KiCad. It's also FreeCAD doesn't have the ability to read them in, and what is even worse is that they don't report what the actual error is. The best thing I could find was FreeCAD basically saying that what was the word? System? No. I think the top level structure, I now don't remember. It was something about model is abstract, and so it cannot load it. So the error itself is pretty non-obvious, especially because this is the whole model. And yeah, and anyways, software that doesn't generate proper errors is just infuriating. Well, the workaround for this is actually downloading the step model, I think. I'm not sure what I downloaded. It's like, yeah, I think it was the step model, and then opening it in FreeCAD and then exporting it to VRML. That was the way to do it. The other funny part is that for some reason, the step model, when I import it into FreeCAD, it is scaled. It is imported, I think, in metric, but the model is in imperial units or something. So it is completely scaled up. So you have to scale it and rotate it within KiCad. So if you look here, in 3D settings, yeah, I had to convert the size to 39 by 3937. So yeah, I don't know, and I could not find a good way of importing it into FreeCAD with the right measurement system. The only alternative, because FreeCAD doesn't allow you to scale models, which makes sense, because if you have a model you want it to stay a real size and you don't want to just arbitrarily be able to scale this stuff. But there is a clone command in the draft system that allows you to scale stuff. So anyways, I would have had to go through loops and hoops 10 times before I get the right size of the model. So again, I was too lazy, so I just scaled it in KiCad. Yeah, I can't wait to see support for the step. Now I'm really not sure if this is the model size format. But anyways, step support in KiCad for 3D models directly, so that you can load them directly. VRML is a weird choice in the first place. Okay, so 3D model, but it looks nice. It's nice rendering. It's I think very sleek and beautiful. And I added some more silkscreen on the back with some company branding. Oh, hello, Micah. Yeah, so the model is there. I think I have everything for the models except the QFN, where, as I said, I was lazy. So that is the FX2 3D. And now let me show you what I did else. So one other thing was to prepare for the, so I already ordered the Gerber files. So basically I exported the Gerber files using the Gerber export. So that's the plot button. And what I also need for prototype assembly is a sheet of paper, as I showed you before, something like this, that I have for a different project. And that will allow me to look at it, put it on my desk next to my microscope, and put the parts really quickly on. So the most important thing is to see the values next to the components, because this thing is so tiny that putting it on the silkscreen directly, what you usually do for through-hole component designed boards, this is on paper as a separate sheet. So what I do is put all the labels and values on the fab layer in KiCad. And with that fab layer, it is possible to create a legend. So if you see, there is a complete overlay, all in yellow, with the numbers. So the item names, this is not really necessary for my prototype assembly. What I'm more interested in are the values themselves. But if we have them and we have the space to put that all together, that's fine. So now if I go on print, I'd have pretty much everything disabled, all the layers. All I leave is edge cuts, bottom courtyard, front courtyard. That's the, yeah, okay. And front fab layer. So with that, if I go on preview, and scale it to the size fit on page there, preview, I get this nice piece of paper that has all the values next to the components. They all have nice outlines. And so it is really quick to just look at them. So what I also do is, after printing this out, I take a few colorful markers and color the most used components in colors. So for example, the 100 nano, I all mark in one color. And then probably the 2K7s, because there's a bunch of them. There is a bunch of, yeah, so the parts that are recurring, I mark them in one color. Then I know how many to pull out of my so-called magic box. That's my magic box. Yeah, my magic box with components. And then with that, I can just, after putting solder paste onto the board with a stencil, I can just place the parts one after another really quick and put them in the reflow oven. So anyways, that's the explanation of the process. As I said, I want to make an edited video of the whole process of the FX2 creation from start to end, at least to the first prototype, and we will see where it goes after that. And thus I will, and because of that, I want it to be the whole process. I am not creating the edited video yet, because so far we only have me assembling or creating the schematic, creating the board layout, doing some cleanup. I also recorded that as an off-stream thing, just recorded the clips. And next, I have to figure out how to set up a camera on my microscope or next to my microscope. This will be an interesting thing. In worst case scenario, I probably will get a new microscope head that is simulfocal, so I can put a camera onto the microscope itself. But I have to think about that and figure things out. But maybe for this project, we will just use a separate side camera to show you that I'm assembling stuff. Yeah, so that I think wraps up FX2 update for now, and we should just move on and start working on the next project. We are waiting for the PCBs to come from Oshpark for FX2. They should be here sometime next week. And the stencil should be here any day. They probably will be here on Monday because our stencil is super quick. There will be, so David is asking if there are mounting holes. No, there will be no mounting holes on this. It's like there's no point. It's a logic analyzer. It doesn't need mounting holes. It's not a device that you mount into something. So it's not an autopilot or something. So I don't think there is a need for mounting holes here. What next? Next week there will be PCBs for the FX2Grok, and I will probably not be able to record anything because next week is B-Sides Portland. So if you're somewhere in the area of Portland, make sure to come because admission is free as far as I know. Or even the ticket is very, very affordable. There will be a lot of really good speakers there. Micah is, for example, has a keynote there, which I'm really looking forward to. Then a lot of our friends, Chris Pavlina will be there, then Kate Temkin will be there. So it will be a big party over there. So I recommend that if you are somewhere in the Portland area, you look for B-Sides PDX and join us there. I will be there too, and let's get some beers. Okay, that's some announcements. Yeah, I think that's about it. Let me catch up with the chat here. Yeah, Chris needs some headphones to hear me. Okay. Anyways, Vince, hey, you're here too. That's nice. We have a few people around. So, if you want to chat, just join the Gitter chat. It is at gitter.im/esden/live. And if you have any questions, let me know. Okay, so the new project, while we are waiting for the boards for FX2Grok, is something somewhat similar that I really wanted to work on for a while, and I was being bugged by a bunch of people to start working on this. So you might know, this is an, let me just switch really quick here. So this is an evaluation board for the FTDI 601 USB black box like transceiver. It's a FIFO. You connect. Come on, focus. You can do it. Yeah, there you go. So this chip can take USB super speed in out, and convert it to a 32-bit parallel bus. That is really quick. So it has a really high throughput. And this will be one part of our system. And the other part of our system will be the very cool, it's like the chip itself actually has the wrong name because the company got bought by Lattice. So it is a Lattice ICE 40 FPGA. And what we will do is, in this case, you see this is a classic FTDI chip. But we will be building a board that, instead of using a 2.0 USB FTDI chip, it will use an USB 3.0 super speed FTDI chip. And basically this will be a high-speed parallel data, like binary data pipe to your PC. So you can read and maybe even write parallel data in out of the computer really quickly without much buffering. The idea is, so the reason why I started looking into this is twofold. So one thing is having a very nice pipeline high-speed logic analyzer for KiCad. So that's where the FX2Grok parallel or like expansion comes from. And the other thing is Mubes. He is at the BitMagic Pro project. He is working on a bunch of very nice tools to parse trace data from ARM chips, which allows you to do profiling of your code without invasive stubs. It gives you ability to communicate with the ARM chip really well. The problem is that logic analyzer or the JTAGs that have tracing capability, basic capabilities are usually available in most logic analyzers, JTAGs. But if you want anything that can actually trace the full speed data, I'm just realizing that my audio is peaking a lot here, so maybe I should do a quick live adjustment here. Will that help? I hope that will. Oh yeah, I think that, yeah, that should help. Okay. Yeah, so he created Orbiculum, which is a parser that can take in trace data from an ARM chip and convert it to useful data and make analysis on it and visualize it and stuff like that. He made a bunch of very good patches for BitMagic Probe to allow low speed, and it's useful, especially for statistical data acquisition, if you want to see how often a function is being called, so you can see. The problem is that if you have the program counter and you want to just completely dump it at full speed to the PC, this is a lot of data, and the BitMagic Probe was not designed to do that in the first place, so this is a little bit shoehorned in there, and thus it's not as fast as it could be, and you have to decimate the data on the ARM side, which there is hardware for it, it can do that, so it will send only every 100 CPU cycles the program counter, so you mostly get statistical data of how often a function is roughly being called. So it's still very useful, but we can do better if we can actually get the complete data stream out. Currently, Mubes got the Lattice eval board so far that he can use USB 2.0 to dump the data. and he can read it out, but it's still not fast enough. So that's why we are working on this. So we will be getting out of this project two applications for now, and I'm sure there's more, is a high-speed logic analyzer and a trace, ARM trace device. So, all right. What do we do next? So I started on this schematic. I did only very few things here, but what I did is, let me just go here and then open bump. Yeah, so the new device, the working title is BitMagic. I don't know if that's good. If you have better ideas for that project name, let me know. The other idea was BitRock Magic. It's like because it's KiCad and 1 bit. I don't know. So yeah, what I did is mostly get the FTDI chip pinout symbol. I did that part. Not sure I even have a footprint for this. I don't. I created this schematic symbol, which is a broken down symbol for the ICE40. Oh, the interesting thing is, so why the ICE40? For now, we are not sure if we will be able to get everything we need into the ICE40, and we are not sure if it will be fast enough. But we want to see how far we can push that chip, because we would love to have the whole firmware and bitstream open source and use open source tools for it. The FTDI chip, I'm aware it's a black box, but I feel somewhat better having a completely like digital black box than using something like the FX3, which would need firmware and a binary blob to carry around. Because parts of the FX3 stuff, as far as I know, for USB super speed requires a proprietary binary blob that you have to load into this. So I would like to avoid having to handle that. So that's why we are looking into just a completely black box device. For now, we will see. It's just the first prototype. We are starting here, so we will see where that leads us. So the FTDI for the ICE40, we have the amazing toolchain by Clifford Wolf. It's Yosys, Arachne PNR, and IceStorm. So this is a flow which allows you to do the Verilog to synthesis. Then it is a place and router and bitstream generator. So we can get complete flow with open source tools from HDL, Verilog, to a binary stream for the ICE40, because he went all the way and reverse engineered it. What it also means is that we can use the ICE40 4K that in theory has only 4K LUTs, but it turns out it's the same silicon in different package and with a different label than as the ICE40 8K. So we will be able to use all 8K LUTs, because the open source software doesn't create that limitation. It's only in the proprietary software by Lattice. And we will be able to use it in a package that is not available for the 8K. So we want to use a TQFP here, a 144-pin TQFP, which is easier to solder than a BGA, obviously, but if we have to, we will go for BGAs. But for now, we don't need to. And unfortunately, the 8K ICE40 doesn't come in that nice package. So that's why we we chose to go that route. Also, it should have enough pins, the 144 pin device. But if that doesn't work out, we can always completely go proper hardware and just go with the Xilinx Arctic 7. That will be probably my next candidate if this is not good enough, because there are rumors that this might get opened at some point. So yeah, it might be future proof. We will see. But for now, let's just use the ICE40 and the FT600 or 601. So the 600 is only a 16-bit parallel bus, and the FT601 is a 32-bit parallel bus, which gives us higher speed than the 600 chip. So yeah, long rant of what we will be working on, and what we have to do is do some basic layout stuff. So for this device, I want to, if we are already designing something new that needs a new connector that is not part of my normal inventory, namely something that can do USB 3.0, I think we should go with a USB-C connector. So I found a symbol for that even. And the USB-C, yeah, some people will be annoyed because, oh, I have cables for the USB 3.0 micro or something, but let's just not try to push for more legacy stuff. Okay. Vince is asking if there are open tools for the Arctic 7. Yes, that would be super cool. No, there are not. Not as far as I know, not yet. But what you can do is use Yosis and output, and use that quite far. And I think you then reuse the place and router by Xilinx. So you can do a bunch with the open tools and target the closed toolchain for now. And if you follow Clifford on, yeah, Dean, follow Clifford on Twitter, and yeah, he's quite a tease. So I think that might change eventually. So. Yeah. Did I answer your question? Yeah, I think. So yeah, for now there are not, but I'm hoping that there will be eventually. Also, the Xilinx tools, it's like whatever the studio is called, for the Arctic 7 is not comparatively less horrific. Yeah, but it is less horrible, I think, and also you can target it as a backend for other stuff that is you don't really have to use their studio then, which is nice. It's still a bit large install, but it feels a little bit better than the web stuff. Anyways, it's still, the proprietary tools are utter garbage and really heavy and really nasty, but. That's why we are going with the ICE40 for now. And if in the future there is an open solution that can target Xilinx chip, that will be awesome, and I'm looking forward to that. All right, so this is the USB-C connector. It's significantly more complicated than the USB 2.0 connectors that had only 5 pins at most. the advantage of that is it is reversible, which is nice, and we have all the additional differential TX and RX lines for USB 3.0 in one connector. And yeah, thank you Apple for donating that connector to the consortium. Why not always like that? The next thing would be also to figure out powering scheme. So the annoying part is we need 3 power buses. We need 3.3 volts for the I/O mostly. We need 1.8 volts for the lattice chip, I think. Is 1.8, and that's for the core of the lattice chip, and then 1.2 volts for the FTDI chip internals, as far as I saw that. We will be going through data sheets a little bit more here because this is, I didn't build something similar yet, so it will be much more research-oriented project in this time around. The other thing that we might want to do is to move the FPGA into its own schematic subsheet, because there will be a lot of stuff going on from here. But yeah, I don't know yet, and I'm saying a lot. Maybe I should stop. Good. So let's just start adding stuff and see where it leads us. I didn't have grid. Let's just start with the easy stuff and connect what we know. We will need ground for the FTDI chip. Oh, right. We can just look into the schematics of the evaluation board. Yeah, so Dean is talking about Xilinx doesn't want you to reverse engineer their byte stream. You are correct, but I'm not sure they can stop you from doing that if you try. Because people already reverse engineered big parts of the previous generations, and there is documentation of that. There are very good papers about the reverse engineered stuff. Chris, yes, there not only was, there is, and they are working on the reing of the 7 series stuff. And so if you look on Reddit into Yosis Reddit subreddit, you will, if you read through the comments, the main comment is that there was some work done on this 6 series already, but there is no point in trying to finalize that project because this is an outdated architecture. So they will be leapfrogging that to the 7 series. And there are already papers and the parts are already read. And to fuzz the cells, you can use the Xilinx tools themselves, which saves a lot of time. So that's why being able to target the Xilinx backend is very useful, because you can then iterate over the fuzzing of the cells very quickly. As far as I understand that, because all the FPGA re stuff is significantly over my head. I can only repeat some buzzwords that I read from people that actually know what they are talking about. like Clifford. So yeah, just let's talk really quick about the FPGA chip, what it is, because I talked about it roughly. What you get is it's a FIFO that can do USB 2.0 and USB 3.0, and it has it's the two PHYs built into the chip. And it has a voltage regulator built in too, which is interesting. And I have to check why the evaluation board has separate power supplies for 2.5 volts and 1.8 volts. This is for the VCCIO, as far as I understand. So we really need to go through the FTDI datasheet. And there is 2 GPIOs, which when we get a little bit into the project, you will realize that it would be really nice if they added just one more GPIO. It would make our life so much easier. But we can work around it. I did some research. That's why the cables are on the board, to figure out if we can abuse some features of the board. Then to get there's the schematic of the evaluation board, and this has VDD, there are several power relays. There's the VCCIO, and VCCIO can be, yeah, so the GPIO pins, if there is no configuration in the FTDI, are being used as configuration pins. Otherwise, you can use them as outputs. So this is what we will be doing. We will use PC configuration software to set up the thing into the right mode, and then use the GPIOs for other stuff. Because one design challenge here is the ability to use the USB interface to load a bit stream into the FTDI, into the ICE40, so that we don't need some special programmer separately or keep one bit stream at a time. So the other big advantage of using an open source toolchain is that you can pretty much distribute it or require it as a dependency for the whole device, and you can then upload a self-modifying or like program modified bitstream into the FPGA to do triggering directly in hardware without having to set up registers and stuff. So that's the idea behind this. And you can just flash the firmware, similar to the FX2, where you upload the firmware for the FX2 from the PC before you start using the device. This allows you for a lot of flexibility and always using the firmware that is matching the software that you're using at the time. In this case, it would be the FPGA bitstream that we would be uploading to the FPGA for whatever tool we are using it for. Yeah, so let's see. We have the connections. Let's add TX. We can connect the USB interface, for example, and the shield can be also connected to the ground, just like we did with the FX2. There is a bunch of I/O protection resistors, 33 ohm, and VCCIO is the power supply. Yeah, okay. So let's see. That will be the shield. We will have to connect this to ground through some inductor or V-bus. Yeah, do we? yeah, we have to connect them separately to each other. So D minus USB D plus. What is the CC2 stuff? Is that charge control? Yes, that's charge control. That's, I think, for USB 3.1 related spec stuff. Because, yeah, I am not that familiar with the whole 3.0 USB stuff. I only read a little bit about it. So I think what the new addition is, they are specifying how the devices can negotiate power exchange, so that that's why not so long ago there was someone posted on Twitter, I think it might have been Snubs from Hack5. She had her Switch, I think, with her traveling, and the Switch ended up charging her battery pack instead of the other way around, draining all the battery power from the Switch. Like, yeah, the negotiation went wrong. So yeah, there is some handshaking and negotiations and priorities, so that you can say which device can charge what. So you can use your laptop to charge your phone, or your phone to charge something else, like your earphones or something. So yeah, there's a bunch of weird stuff going on with the charge control. If we look into the datasheet of the FTDI chip, there is also special modes for charge control negotiation, but I didn't pay too much attention to it, so sorry. Right. Yeah, let's make some more space, then we can get the ground stuff connected nicely so that it looks neat. And that will be ground. And let's start with the power. Yeah, one other thing I was trying to figure out regarding this stream is on the last stream I realized that we were hearing some weird, like, buzzing, like rumbling noise in the background. And it turns out that because my house is not far from a busy street, the rumbling sound is actually cars driving by. And I spent some time today trying to figure out how to get rid of that. But I fail at setting up the audio filters right, so that it would be able to filter out this rumbling noise. So I apologize if you hear from time to time this weird squirrely sound on this stream, but I don't really have a solution to that, besides maybe eventually putting a pillow into the window. But yeah. Yeah, VBus is probably the 3.3 volt, the 5 volt supply. Yeah, VBus will be this. Yeah, the other question is, do we want to even have the VBus? Oh, interesting. Yeah, I could use a lapel mic. Hi, Jared, first of all. And yes, I could use the lapel mic. That would help. The problem is it doesn't... Yeah. Yeah, I will set it up for the next stream and we will try it out. That's not a bad idea. I am currently using my Rode boom mic. that I have for usually camera use, and it's set up here, and it is pointing at me. So I would, the other thing I could try is so that maybe it is picking up the noise from the outside that is coming from the direction of the window, and the microphone is here. So if I move it to the right so that it is pointing this way, that might help too. This way I don't have to use yeah. Yeah, your ambient noise on your end might be swamping it out in the first place. Yeah. Yeah. Usually it is quite quiet here, especially when I listen to stuff. Then it's usually evening. Then the car traffic is also dying down quite a lot. So I don't know. Just trying to make it as good as I can without spending too much time trying to yak shave. But yeah, I can try the lapel mic. It's not bad. It's wireless, so yeah, that would work. Then I have to figure out some good solution for having replacement batteries. I have to get a rechargeable battery, AA battery set up and stuff. I also found that Sennheiser is selling super expensive set of rechargeable batteries that are meant for those mics. Then you can charge them with the two contacts that are on the side of the devices. But I think that's a little bit of an overkill. I just see that the symbol is not aligned to the grid the way I would do it. Yeah, this is why you don't use someone else's symbols. They will always be somewhat wrong. So yeah, I guess it really depends on the background noise, how bad it is. Part of the issue might be that I am really trying to pay attention to all the factors, which as a listener I wouldn't pay attention to. Yeah, and I know that this is a thing because several times other people were complaining about the audio of their videos that they are creating, and they improved the audio, and I was like, it was fine before, it is better now, but I didn't even notice. So yeah, I understand that this might be part of the issue too. Yeah, RX minus. So this is the annoying part. They are all over the damn place. RX2, RX1. So there are two bidirectional buses. The question is, so as far as I understand, there's only one lane on the USB 3.0, and the 3.1 has more lanes. Is that right? And that's why we have RX2, RX1, and TX1 and TX2. So these are two differential lines, and it is full duplex, which is the big improvement over USB 2.0. But yeah, there seems to be, if we look here, there's only one lane. So what do we use? Do we use just TX and RX1 connections? Is that what it is? Probably should. Do we want to yak shave that at the moment? Yeah, we could, but I'm not sure I want to. Yeah, we have to look it up. Yeah, that's it reminds me of a few yaks that I didn't take care of on the FX2Grok thing. I still have comments in the schematic where it says I should check some resistors for the crystal. Yeah, that might be the reversibility. Yeah, does this mean I have to connect RX1 plus to RX2 plus? That's a good question. Yeah, you're probably right, because the D plus, D minus, so the left side, so the A stuff is one way around, and the B side is the other way around, right? So the B pins are if it is plugged in one way, and A side is if it is plugged in the other way. yeah, me too. Yeah, thanks for looking it up. Yeah, the stubs. Yeah, how do you connect this stuff? Because yeah, I looked up one of the connectors somewhere. There is a connector, and it's SMD. So A1 goes to B12, and this is ground, and then you have TX. Yeah, if you look at it, this bottom side is the reverse of the other. And this means that we would, if we connect this stuff together, we have TX plus on the left upper corner, and then we have TX2 plus on the right corner. So if they are connecting to the same differential pair, you get different lengths of traces between one and the other. How the hell do you even route this? Okay, this will be a learning curve for me for sure. Huh. It's not just mechanical? So Jared is saying that if he remembers correctly, I think they sell chips that are complete USB-C interface solutions. Perhaps they perform side switching. Oh, so that you don't... Ah, I know what you're talking about. You are saying that you don't get these dangling traces coming out that act like antennas at the end, because if you put it one way, then it only connects to one set of connections instead of connecting to both of them at the same time. Is that's what you're saying? Yeah, it's like RF transmitting USB protocol over the air using your PCB traces is probably not desirable. Yeah, it would be good to find some eval boards for USB-C and see how they're setting it up as a reference. Okay, VBus. VBus we will call just 5 volts, just per usual. So that would be this. And then we have the USB 2.0 stuff connected. Oh. Okay, Dean is saying that there is a USB 3.2 spec that uses both pairs. Okay, great. So to be forward compatible with this, probably it's necessary to use some kind of a chip that connects. Sneaky future feature, yeah. Yeah, I like that. Oh god. Such a Pandora's box that I opened here. for now. Yeah, cheap interface chip. Okay, let's Google for it really quick. Blah, blah, blah. Lots of text. Give me some schematics. This is charge control mode controller. Audio over USB-C. I don't want to. Should I just use micro USB 3.0 because it is so much simpler? Jesus. This is when you let Apple design something. They completely over-engineer that thing. I love the reversibility, but it just sounds more and more like a nightmare to deal with. This is charge control. One chip solution for USB 2.0. You found it? Okay. 546-DCI. Okay, let's see. Crosspoint switch. Is a Visa USB Type-C alt mode redriving switch supporting 3.1 data rates up to 5 gigabit and DisplayPort. So this would be connecting. Oh, so this is when you need to use USB-C for DisplayPort. Then it uses the other two pairs. That was my cell phone, actually, Micah. That vibrated on my table. But yes, close enough. Oh, Micah, it was you mentioning me that vibrated and made the sound. So, that's what happened. If you mention me on Twitter, you make my desk rumble. It's fine. It's okay. Thank you for mentioning. I appreciate it. Okay, so let's go back to the data sheet. So, and vibrate again. Hey, Jared. Yeah, I moved it to the box next here. It's like I probably should just disable vibrations on my phone when I'm streaming or something. I don't know. I don't mind, actually. I have a bigger problem with the cars outside than my phone vibrating. It's like... Alright, so let's go back. I got distracted. Transition an existing USB Type A design to a USB-C downstream facing port, or any existing Type B design to USB Type C upstream facing port. Upstream facing port. Oh, the language they're using for the 3.0. So downstream facing port is what? Down, it's to the device. Yeah, and downstream is host. Yeah, okay. Okay, thanks, Dean, that helps. So we need to find a reference here that explains this, I think, to make things easier. So yeah, we need a switch. What did you also link? UTC 2000 from Microchip. So this is the TI solution, and the Microchip would be UTC 2000. And that's okay, let's read highlights, transition any, yeah. So that's the UTC 2000 that we're talking about. Okay. Pop, 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 pop. It's the charge control. Oi, oi, oi. Okay, so this is managing the whole charge control pins too. Plug orientation, and it does host enable. Yeah, it's which, because you can connect stuff to each other much more flexibly with this interface. Yeah, it makes sense that they changed the language. It's just I just have to wrap my head around it. That's all. USB mux switch. So this UTC 2000 is not enough. It still requires a mux switch. Page 30. Okay. There. Let's go 30. Ah, nice. USB 2.0 application schematic, but that's not what we need. Oh, let's look at that first. So 2.0 would be just connected like this, and then you have MOSFETs with the charge control stuff, so you can provide isolation FETs when unpowered, and then VBus monitor, so it is monitoring the input VBus voltage, right? No, it's output. It's VV out if you want to power something. Okay. VN. That's an with audio adapter application schematic. USB 3.0A charging port AC adapter application schematic. So that's the power adapter. UFP. Device application schematic. Okay. So we still need the USB 3.0 switch. That will take the multiple lines and convert them to single lines. Okay. And would that be a switch? It says redriver crosspoint switch. Yeah, so this seems to be... Oh, okay, so basically the UTC 2000 is the PD controller. And what we have here is the crosspoint switch. Yeah, I think page 31, UFP device application schematic, might be close to what we need. And it shows the plug orient. So this is the plug orientation pin that will be driven by the UTC 2000. And this will connect to the correct set of pins. Because these guys are easy, the USB 2.0 stuff. And then we have the charge control pins that are connected here. VDD, enable, to system, current sense. There's a current sense op-amp here, I guess. OCS, so another chip. So we need 3 chips to use the USB-C connector. More actually, because we need some FETs and we need a bunch of passives too. Yeah, it does look like a normal comparator. Probably is. To do current sensing. I'm not sure I'm a fan. It probably would be much easier to just use the stupid. Now I understand why I can't find any USB-C eval boards out there, because it turns out to be a complete nightmare to set up, and it requires a ton of chips. Guitar truck? I don't know. It's possible. Yeah, it's weird audio artifacts that are being created here. I like that. It's like Furiosa is coming on a truck down Eugene roads. Okay, now let's see if there is any so Intersil is a company I could imagine having something useful. Because they usually create affordable and quite integrated devices or sets of devices. Yeah, USB port power supply controller, USB-C, battery charging. Yeah, I don't care. That's Renesas. Yeah. Does TI have like a reference design for this kind of stuff? That would be probably easier if they just had a schematic here of what one would do. So yeah, this is the mux for sure. Let's see if there's a reference schematic somewhere in here. AC coupling capacitors, okay. So you would AC couple this stuff to that chip from the differential lines. But that's the layout. GPU, but this is for GPU. Yeah, I think I have to postpone dealing with this for a little bit later, but yeah, I think USB-C, yeah, and make the decision if I even want to go USB-C route at all, because This is a bunch of chips, but okay. For now, we have USB-D, and we should just continue labeling stuff that we will need to use. So this is I know that the GPU is for a graphics card and DisplayPort application of the USB-C switcher. The question, I have to read through the data sheet in peace, but probably not on stream, to wrap my head around the fact if I even want to use it. Second of all, what do I actually need regarding support chips if I decide to go with USB-C? And all this stuff, because do I need all the charge control monitoring crap on my device because it is not battery powered and it will never supply power to anything? It is always a slave. Are there... Micah, exactly what I'm talking about. I want... Sure, we can add one chip to do the crosspoint switching. Sure. Is there a chip that can just do the basic device with no battery management for the USB-C connector and done? It can't be that hard, I guess. It's like all you need is to connect this stuff together. Yes. Okay, we can name this because we don't know what is going on here on the left, but we do know that we will need these. Oh, come on. What's going on here? Or a chip designed for USB-C dongles. Yeah. That's why I was hoping that if I look at Intersil, there will be something, because they are known for creating just a small, ultra cheap solution for a specific application. So, yeah. Oh. Okay. Let's see. TI. What do you have? 2-channel differential, mux demux. Yeah, this is the moment where I need more than one monitor capture for for the stream. Mux demux solution. Oh, nice. Yeah, but okay. And how? System host controller, connector. Down facing, up facing. Oh, this is where the capacitors are set. I should, this is close, if not what we need. It still is talking about the stupid charge controller. Yeah. How does the... That's down facing. Typical application, down facing port. And then up facing port. Yeah, it's also a charge controller. Huh, interesting. Oh yeah, Jared, no worries about TI. That's fine. TI has quite a decent search system for this kind of stuff, and they usually have the solution. Yeah, the question is regarding the parts that you guys are proposing is the controller. Oh, this one. Oh, Dean's part has a charge controller built in. I see. Okay. I'm getting excited. Now, hey Anonexus, welcome to the stream. We are looking for a solution to connect a USB Type-C connector to a USB 3.0 part. It turns out, which I didn't know, that you need something in between that does the reversibility. Okay, Jared. Yes, that makes sense. So Jared is saying that his doesn't have a charge controller because it's minimum price. Yes, that makes sense. Yeah, I think. Yeah, it does seem like fun. It is fun because I didn't realize that using a reversible USB-C type connector is so much more complicated. Yeah, so lesson learned. But I think we should just give it a shot because with the part from the family that Jared found and Dean narrowed down, we might be able to solve it. So ti.com lit ds symlink hd. Oh, it's all large. Jeez. Should I just open Gitter? Let's go there. There we go. Okay, so this is the chat. Now in large. Let's open it up. Okay, so this is the part. I don't have the chat from YouTube open on this laptop either. I don't have any chats open here because then I get pop-ups like this. So I am closing this again. Yeah. Yeah, I'm paying attention nonetheless. I have the monitor up here with the chats open. It's just opening links is a nightmare. Well, not nightmare, it's easy. It's like you just have to open it up real quick. Okay, so I think this is our solution for now. Unless we find something simpler or more affordable. This seems to be, let's see. Let's look at the short schematic because I saw it already. Yeah, there we go. So this part has I2C for the controller. I will have to figure out what that does, why we need I2C on here. Then it has GPIOs. Oh, so you probably can expand GPIOs on this? Okay. Then we have, yeah, so I am, when I see the I2C interface, I'm getting concerned because we might need some external data input or configuration for this, which would be bad because the device is mostly passive. But it has the charge control management stuff, and it has the mux built in. So, so yeah. This is what we would look into. Yeah, let's see what this controller does. Maybe yeah, I'm trying to skim as much as I can, and then I don't pay attention. USB-C, host only, device only, dual role port. Ah, I see. So UFP is what we want, device only. Cable orientation detection, role detection, USB-C current mode. configuration control through GPIO and I2C. Oh, so we can set it up just fixed with the GPIOs. That's nice. That's my scroll wheel. Okay, yeah, that's possible. Or the guitars on a truck. That's my scroll wheel. Maybe that's what Micah was referring to. Is my scroll wheel. Squirrel wheel. Oh, that's nice. That does this. Yeah, let's look for a reference schematic, typical application for UFP. Oop, there's some schematics. What is it? DFP, no. That's dual roll. And we need a badam UFP port. Good. That's the connector. DP SCL SDA. Yeah. So this wants I2C here, but why? Can be used to design USB UFP port. Example schematic UFP port implementation. Does not care about differential pair polarity. Oh, that's nice. Okay. PCB. Oh, this one even has stack up requirements. 6 layer. Oh, yay. Yeah, are we getting into 6 layer territory with this design? We probably are. I wish Oshpark had 6 layer, but it's difficult. Yeah, I think I should be able to get away with 4 layers on this. I'm talking about bias, so it's mostly signal integrity related stuff. Layout. That's very generous that they put all this layout guidelines on here. That's useful. Yeah, so my problem here is, yeah, I'm eating carrots again, so let me stop eating my carrots. DFP, I need to... So what we need to figure out is what this I2C stuff does. I2CIO. Yeah, I assume that I don't need the I2C necessarily, but what I need to figure out is how the GPIOs have to be configured if we don't use them. And I am trying to find the section of this data sheet. That's the... yeah. But I would not tell you, I would just hide it in plain sight. That the device we are building will get all your private data and send it to my vault. Okay, configuration, description, table of contents. Let's look at the table of contents. Dual row, power supply, device functional modes, unattached, USB port attached, ID, port operational, I2C on. Okay. Yeah, so Anon Nexus, this is DDoS by anime. Or DOS by anime. Hi Bob, nice to see you here too. Yeah, regarding the I2C and how to configure the GPIO, will probably require a little bit more research, and I'm not sure I want to do it at the moment. So I2C GPIO, DRP, not connected. So it doesn't care if it is low. Oh, so for dual role, yeah, they have to be, oh, low, I see. Can be configured DFP, UFP, or DRP using three-level port pin. The port pin should be strapped high to VDD5 using pull-up resistance to achieve DFP mode, low to ground to UFP mode, and left floating for DRP mode. Okay, so we have a solution here, so that's fine. Yeah, so yeah, I think we have a solution. I think this chip will do, unless we find something else that is not it. But yeah, this means I need to make a symbol for this, and then we have to make a funky footprint because this is a funky QFN. Yeah, QFN. Okay, so VQFN 30 with funky funk. All right, so we have a solution, so we know where this is going, but for now we will just continue adding pins, and I should probably just move this. And we will just add a note, add, how is it called? I want a name, HD3SS, HD3SS, 3220. I might use someone else's symbol or not. We will see. I am skeptical of other people's symbols, but yeah, it could be a good base to create our own. So yeah, I will do that. Okay, so VDD1. We should look at the schematic for the. Oh, we wanted to add the data names here. USB. TX D minus. D plus. Oh, interesting. So the I2C, so I2C here is in master mode or like report mode, so you don't have to use it. Okay, yeah. So that's what I think is going on. That we don't really have to use the I2C interface. We can just strap the pins to certain levels to configure the chip for a static application like this. Dim plus. Okay, so we have these added, and they will be connected to the HD, and then we have the USB-C interface, and we will be adding those. So we can actually label those too, and just have them be part. Yeah, we can add the labels to those pins because we will be using them. The question is also, what I didn't figure out is what SBU1 is. SBU2. Serial, right? That's what it is. Something. Okay. And more learning about USB-C interfaces. VCC-IO. So VCC-IO, let's look in the, there we go. So we have here all the VCC 3.3 stuff. VCC 3.3, VCC 3.3. They should be connected to 3.3 volts. VDI 10 is because this comes out of the LDO V10. So we have a built-in voltage regulator on the FPGA chip that has an LDO that has output of 1 volt, and this will go into this stuff. It needs some decoupling capacitors, so we can strap this together, and then we have VCC-IO. What is going on with the 3.3 volt stuff? .3 AVDD for the PLL. I see. So the PLL analog voltage input goes through an inductor and then has some cleaning and then goes into the analog input. Oh, interesting. Thanks, Anon Nexus. So the SBU wires, the ones that I was asking about, where is it? There. SBU1 and SBU2 is wires are lower speed signal wires that are allocated for alternate mode use only. USB power delivery is required for alternate mode negotiation before these pins may be used for any purpose. I see. So, yeah, that's an additional feature that we probably won't be using because we are not doing power negotiation. Okay. Here at the ground, we can copy that over. GPIO will become interesting soon. Then we have a crystal here that we will have to connect. The crystal has to be a 30 megahertz crystal. Yeah, let's do, in which order do we do this? Ah, I see. So let me just do this first. And name this stuff. Do we have a 1.0 volt symbol already in the power? Or do we have to make one? Yes, 1V0. Let's see if there is a better one. No, I think this is fine. 1V0. Yeah, 1V0. Okay, 1V0. Okay, the AVDD needs some filtering and then be connected to the 1V0 stuff. Then the 3.3 volt stuff. How does that work? Do we have a voltage regulator on here for the 3 volts, an external one or not? Because VBus comes in. It's probably on a different page. Let's see. This is connectors. Oh, this might have been before this page. Let's see. Yeah, there we go. Yeah. Okay, VBus is connected through an inductor, through some capacitors, to a voltage regulator, a 3 volt voltage regulator, FMC, HSM, okay, HSMC, so this refers to the connector on the back here for the FPGA board that this eval board is designed for. This is for Altera FPGA boards. And you can either drive it from 3 volts from the HSMC connector or from VBus or the barrel jack. So we need a 3.3 volt voltage regulator to generate the 3 volts. And then we have another voltage regulator that can either make 2.5 volts VCCIO or 1.8 volts VCCIO. Dean, yes, you're correct. I described it a little bit earlier before, but you might have missed it. Yeah. Yeah, the idea is to combine the FTDI together with the FPGA to have. It's a multi-purpose thing. It's a logic analyzer as well as the useful as a pipe for ARM tracing outputs. Yeah, so that's the idea. But yeah, this requires quite a steep learning curve for me because I have never done a bunch of this stuff, like dealing with the USB 3.0 or laying out high-speed parallel signals and stuff. So this will be interesting. And it will take a while. Okay, so let's get the 3.3 volt stuff copied over from somewhere. And the question is, I think the FTDI can run this VCCIO. Let's look at, yeah, it can be VCCIO supply voltage. This is absolute maximum. I don't want that. I want the standard, like typical. Yeah, 3.3 volts, VCCIO 1. What does that mean? DC's characteristic, ambient temperature, conditions, VCCIO 3.3 volts. Oh, this is the outputs. operation. Yeah, so we could just run it on 3.3 volts completely, right? We don't need the 1.8 volts here, as far as I understand, because the internal 1.0 volt core supply regulator is already built in. Yeah. Probably then we should have all those boards just have a built-in and an attached fire extinguisher directly over the chip. Or put it in a blast-proof case, so if you plug it in and it explodes, it doesn't hurt anyone. That's a solution, I guess. Okay, AVDD. So we can run everything on 3.3 volts. The only thing I need is the AVDD management here. A 1.0. Oh, what about putting this as a separate thing? 1.0 VA, the analog. 3.3 VA, this exists. Come on. No, of course not, because why would we? There's a 1.0 volt, but there's no 1 VAO. Okay. Anyways, let's because this should be probably longer, we can create the necessary wiring there. Oh, is it AVDD and then or VDDA? Oh, they differ, right? There's like two very confusing pins on this guy. One is VDO, where is it? VD1. Now I'm blind. I really can't find it now. The analog stuff. Where is it? Oh, this is the FT600, not the 601. Okay, that was the problem. The two schematics are next to each other. PLL AVDD. So AVDD is one, and then VDDA. Where is that? There, VDDA. That one is connected to just 3.3 volts. Oh man, why are you doing this? Yes, 28. So this is 3.3 volts. Okay. Let's put the 3.3 volt label on this. V3. 3 V3. There. This one is easy. Yeah, I think I organized those pins because I ran into this confusing issue before, and when I was making the symbols, and that's why I put this close to the 3.3 volt stuff. VCCIO, let's, yeah, this goes to 3.3 volts too, as we figured out. And VBus. RF, we need a 1.6 kilo ohm, 1% on this one. And the reserve pin also needs some magic. Reserve there. And say connected with 33 ohm to this, which is pulled up to 3.3 volts, right? dB. Oh well, we will do that. Okay, I'll be right back. Just need a short break. Okay, be right back, guys. All right, I'm back. Alrighty. So, where were we? We were adding a bunch of the power supply stuff here. We know that the reserve was a weird thing. Oh, let's look at here. It's the question would be actually to check if this is actually connected here, or 13, because I've seen a bunch of non-populated parts on this eval board that seem like they're needed, but then they don't put them on there. Or 13, or 33. Oh, yeah, wait. Or 13. 13. Yeah, there it is. Yeah, it is connected. Okay. So it needs to be pulled up, I guess. Yeah, we could also just grab it too. Okay, so we need to add a dipole, device, PKL R small. There. Let's set it up because we will be copying it as usual. Footprint, just assign it while we're already at it. PKL dipole R402. And reference doesn't matter, and this was 10K, I think. Let's check. Oh. What is the pull up? 10K. Yeah. All right. Move. And it's pulled up to 3.3 volts, right? Yes. Do we do this like this, or should we make it clearer by... Yeah, we should make it clear. Okay. .3 volts. RF. So the RF was this weird thing, 1.6 kilo 1%. K6 1%. Right? I hate when that happens. So align right, move. There we go. We should probably give it a name so that it is reasonably readable later when we lay out the board. RF. Rough. And it goes to ground, yes. Name it Bob. I'm not sure Bob will appreciate. He's on the stream too, or he was at least. Although it could be a tribute to him. It's like you got a signal named on the board. Okay. VBus. There we go. VBus in. Let's see. Well, you are the only Bob that I know, so yeah. I think. I don't think I know a second Bob yet. Since I don't remember. Yeah, this is a thing I like about the PDF viewer on macOS better, because you can rotate only one page of a document and not the whole document. Makes it nicer. Okay, we have the 3.3 volt supply, but there's the in. Yeah, where the hell is it? Does it have a separate regulation here? Or like a voltage divider or something? VBus in. Where is it? VBus in. There is a resistor network. Okay, so it's a voltage divider. 4.7 and 10 kilo. Okay. Huh. Interesting nickname. Okay, so let's do this. Let's just name the signal we need to copy this, copy, make 2 of them. Oh, the V-bus is actually the 5 volts. Okay, yes. Copy. Move. Yes, probably will all go together on a power supply sheet or something. Yeah, I don't know yet. And ground. Okay, so what did it say? 4.7 and 10K. 4K7. And then look. And copy. There we go. So we have that sorted. This is not centered. It's annoying. We could also add the connection here. Do I have something that would? Do we have a symbol? Connection device. Yeah, L small. Is that something we should connect? Because there was some discussion that I'm doing it wrong regarding connection of the shield to the ground. I don't remember what it was exactly. Let's look really quick. Probably there will be something in this schematic now. Unless they don't care, that's possible. Or we could look actually here, what they did. Yeah, they added 2 resistors. And they are both 0 ohm resistors that are connecting the shield. Ugh, it's weird. Yeah, because I thought about connecting just a ferrite bead here to the ground. Usually these are 600 ohm ferrites. Okay, anyways. Copy. It's just temporary. If it sucks, we can put something different on there. Yeah, it doesn't make sense to me. Noise suppression with 0 ohm resistors. No. Probably not. Now it's more aligned. Yeah, this whole symbol is all over the place. Yeah, look at that. This side is not even aligned. It's like this one is aligned. It's not. Ah, I have to edit that symbol. Fix the symbol. That's why I don't copy stuff from others. I was lazy. Right, so V-bus in. This side is pretty much done. All we need is the crystal now. Yeah, Jared. Yeah, that probably makes sense. They usually tend to... Yeah, this is a good question. I could look actually at the board. So it is R28 and R29. R29, R28. They're on two sides of the connector. Let me look at it. Yeah, these are definitely 0 ohm resistors in this case. They're both just connected 0 ohms to the sides of the connector here. But yeah, one could just add ferrite beads, I assume. Optional inductors. Yeah, weird stuff. Okay, where were we? The AVDD definitely needs love. This is definitely something that will have a inductor here and will be connected to the 1.0 volt system. Copy. And we will have capacitors. What do they recommend here from the datasheet? Yeah, the datasheet doesn't mean it's the right thing in general either. It's a good reference to start with, and we will be able to adjust it in the future versions of the schematic. So this is 47 micro, no, so it's 470 nano, 470 nano and 100 nano. So 100 nano capacitor. Wrong click. PKL device, capacitor small, please. C small. Edit, and this will be 100N. And footprint, we can just assign it because this will be everywhere. Okay. And we need, they say 470 nano. Do you want to make it, let's see what I have in my magic box, because this tends to be a good indicator of what I typically have. 470 nano, yeah, 0402s. Yeah, let's put an 0402 here. Copy, and just change the value. Edit. 470N. These are normal packages. It's not small, it's not large, it's just normal. 0201s are pain, so that's why I'm not using them. I think 0402 is a good compromise between laziness and practicality. Oh, what did you do? There we go. There we go. That's far enough, I guess. Dean, that's a good point. The interesting thing is that I rarely see this stuff. The only design so far that I've seen some proper, quote unquote, I don't know if it's proper, but some more complicated parts between the shield and the ground plane is the Salia logic. That's all I've ever seen. Everything else is either just directly connected to ground, maybe have 0 ohm resistors. In rare, maybe I've seen an inductor once, but otherwise the most complicated thing is this stuff, and I think it has a capacitor and a resistor, and it might even have a fuse where it is connecting the shield to ground. So that's why this is people rarely talk about the difference. The clones in China of the Salea logic don't have any of those protection things, or very few of them, and this thing has all the work and energy put into making a proper hardware design. So it's just sad that no one, like so few people care about these things. That they basically had to completely ditch that product line and make much more complicated and expensive devices that are not really compatible with KiCad anymore and stuff like that. So yeah, sad. Okay. Yeah, I have a strip of 0201s that I ordered by accident a while ago, and I even have the soldering challenge that I got from Drew Fustini from Beaglebone or Oshpark. He gave me one of those. I should finally assemble it. I probably will do that as a test of my microscope setup if I have that finally. And there's these are LEDs starting like 1206 parts and then going all the way down to 0201s, all these steps down in package sizes. So this will be fun to put together. Okay. It's not cheating. It's just using proper tools. I'm even planning to do it with the soldering iron instead of using a stencil. So I think I'm doing it as intended. And it's like if you are into electronics and don't have a microscope, then it's like I'm sorry for you. Yeah. It's like just like a soldering iron, I think the second most important thing is having a microscope. Yeah, it's true. Okay, so what... I envy your quality of your eyes. Anyways, so where were we? I need to copy over the 3.3 volt stuff. To do that, now I have to think, do I have to open the schematic as such? And will it be able to copy it between 2 sessions? That's what I'm not sure about. It might have been, because cut and paste from schematic to schematic is a little bit interesting. Okay, so KiCad flat, save and exit. Let's go to the schematic and copy these 2 things, because up this and this. Copy block, then file, pen schematic sheet. This is what I'm not sure about, if this will work. I don't think it will. Edit. Okay, let me think. There was a way of copying between schematics, but how do I have to do that? Yeah, so cut and paste. Cut selected item. Oh, so maybe I did it wrong. File, open recent. And then select this. Maybe save block. And then open the other project. Yeah, no, it doesn't work like that. Ah, damn. Okay, so do I have to open the schematic separately? schema, and then BM1 like this, and then open recent. I do this. Yeah, oh god, okay. So this is how I had to do this. Yeah, cut and paste in KiCad is a little bit tricky. So I know it's another nightly build thing that they're working on. I don't know if it is merged yet, but I was reading on the KiCad developer mailing list that someone was fixing the issues with cut and paste. I'm not sure if it was related to schematics or board design, but you should finally be able to cut and paste things between stuff easily. But yeah. Okay, save and exit, and let's open KiCad again. Yep. All right. So we have Xtel in, Xtel out. Let's name it like this. Okay. And we should adjust the frequency of this one. This has to be 30 megahertz. 30 megahertz. Yeah, and check Xtel cap values, of course. What we can also do while we are already at it, go to DigiKey and search for with an H, oh, whatever. Crystal with an Y or something. I should learn English, it would be nice. Oscillators, oscillators, crystals, oscillators, resonators, and remove the search. Crystals, and it's without an H. Okay, good. Yeah, it would be nice if I learned English. That would be nice. Okay, so what I usually use is Abracon, and all I wanted to see is if there is an ABM8 package for the crystal I need. 30 megahertz. 30 megahertz. Apply filters. ABM 10, 12, ABM 8, perfect. Nice. And what is the load capacitance? 18 and 10 pico. Yeah, we can set this to 18 then. I know that actually what you do is you take the load that is intrinsic to your PCB, as well as the outputs of the chip, and then you subtract and make just these values will have to be adjusted based on the overall performance. But if you just use the load capacitance directly as the value of the capacitors, I have found so far that just seems to work well enough. So yeah, lazy again. I think this is the main story here. Lazy. Okay, so we have the crystal, we have 3.3 volts and the 5 volts, and we should not call it FX2Grok, it's just 3v3 VREG. And this should be called FT600 clock. Okay. So this is set up. Now, next, something I never used is use a bus entry, place a bus and have bus inputs, outputs. I'm not exactly even sure how this works in KiCad because I've never used it. What we can do, I think, does it, Jared, if you are still here, have you used the buses before? Can I just is this mostly a graphical thing in the schematic, just like in Eagle it seems to be the case? Because in Eagle it is mostly just a graphical eye candy and nothing else. You still have to name the signals one by one. But yeah, we will need this. Oh, so it is just graphical eye candy. Okay, good. Yeah, so I have to create all the... Yeah, so I have to name all the signals, what they are, then I can use the bus to indicate where it goes, and that's pretty much it. Okay. Oh, sounds like fun. So the interesting thing, I'm trying to think what how to set it up here, because to get the bit stream loaded into the FPGA, we have to use this SPI interface. And this SPI interface will be connected. So you can reset the device with the C reset B, and then it is, depending on how it is configured, it is in different... Okay, thanks, Jared. If it looks horrible, you tell me, please. Yeah, we should probably do the power supply stuff here on the FPGA next, because this is easy. We can also create the data bus entries. And okay, so what I was talking about is the SPI bitstream loading. So what we want to do is be able to use the FTDI chip to load the bitstream. So the solution that we came up with is use one of the GPIOs to reset the FPGA so that it goes through its state machine, and we can then use the SPI interface to load the bitstream from the FTDI chip. The problem is that the SPI interface requires data in and S clock to get the bitstream loaded, as well as the reset pin. So if we had 3 GPIO pins, we could just bit bang that data in. Because we only have 2 GPIO pins, we have to do something different. And the idea is to use the lowest significant 2 bits of the data bus coming out of the FTDI chip as SPA clock and data to the FPGA when it is running, when it is reset and waiting for bitstream input. This means that basically we will be sending multiple packets or multiple bytes of the same data to create a slower frequency data input to the FPGA, because I bet this can't handle the full frequency that the FTDI chip would output as SPI input data. Yeah, also what is interesting, the FTDI chip continues generating clock while there is no data available from it. It indicates if the data is available or not on the TXEmpty, RXF pin. Again, depending on which mode you are running it at, which type of FIFO you are running. If you are using the old type of FTDI 232 chips, then it is passive and you can just dump data. When it is running in the new FT600 protocol that can support multiple channels of data, you have to send a few bytes of data to the FTDI chip, which channel you want to read out, making it not passive. You have to actively request the data. So the FTDI chip has to be configured in the legacy 232 mode that is only one data channel to transfer the data to the FPGA, so that we don't have to have any active components requesting the data from the FTDI chip. All right, anyways, long story. But yeah, that's the solution I came up with to be able to load the bitstream and be completely passive and not have to add a microcontroller or something that can manage the whole thing. Yeah, so we will be bit banging the SPI data by sending multiple bytes of bits to the FTDI chip from the computer software with like multiplied and transcoded data to the bitstream. We can do that because, you could do that actually with any device, because usually the protocol how to load a bitstream into a device is usually documented. So even if it is a Xilinx or something, you would be able to implement that. My thought was, oh, this is nice because we have an open source documentation for this. It wouldn't matter even for a proprietary device because it's documented. Yeah, so Bob is asking if the FPGA can't implement any packet configuration protocol. What we are talking about is how to load the bitstream in the first place into the FPGA when it is empty. We can't just do any arbitrary thing because first of all, the lattice, it's more complicated than this. We could theoretically implement some kind of a payload in the FPGA to be able to read data in and put it in the FPGA configuration memory and then reset itself in theory, but this makes it so much more complicated. Yes, that's what I'm talking about. There are 3 modes for the FPGA. One mode is load some static configuration that can never be changed again within the Lattice FPGA. That's a special feature that the Lattice FPGAs have. Then you don't need any external memory, nothing, but you cannot also change the configuration ever again. That's one mode. Then there is the mode where you have an external SPI flash that will be read out automatically on startup by the FPGA, and then it will configure itself. You can then change that content, and this is how this eval board works by default. You use the FTDI chip. It has 2 ports, and with one of them you can flash the external flash with the configuration that you want to change. And then the FPGA, when it gets reset, it will read out that data out of the flash. The third mode is completely passive, where the host or whatever just keeps the device in reset, loads the data into the FPGA actively, and then it gets the FPGA out of reset and lets it do its thing. So we will be using the third mode to load data from the PC over USB. And because we don't want to have to add additional USB interfaces or additional microcontrollers, we have to hack the stuff that is available on the FD600 to do that. I hope that explains it. So the important thing to make that happen is we have to configure some of these pins that are that would be inputs, to configure them so that this thing starts up in the right mode. We will have to use a PC software to so the FTDI chip has these 2 GPIOs. If you just get out of the factory the FTDI chip and just dump it on a PCB, by default it will use the pull up and pull down on the 2 GPIOs to configure itself. You can set it up as being the old FIFO or new FIFO with like more or less different channels, higher frequency, lower frequency, using this 2 GPIOs. Because we need those GPIOs though to be able to use them as outputs to reset the FPGA and set it up, we will have to use a PC software to configure the FTDI chip. It has some flash in it to set up a configuration for it. And we will do that. We will set it up in the legacy mode. The important thing for me was, and I found it in the datasheet, was to be able to switch from a slower frequency or a different configuration mode to another using the library that FTDI is providing. And it turns out it is possible. During runtime, you can reconfigure the FTDI chip and set it to a different mode temporarily until reset, which is nice. Yeah. Yeah. So we need to, and I should have written it down and I didn't. I think we need to have the output enabled, pulled low, because it's negative logic. So when you set output enable, then the FTDI chip is asserting the state of the data pins by itself. Oh, so because the FPGA is not doing anything actively until it has the configuration loaded, we have to statically pre-configure the FTDI chip outputs that are independent of the internal configuration. So we need to have the, yeah, let me check, what did I connect here? Okay. I connected, is that the 601A? Yes. So I connected some wires to, this is 1, 2, So this is the TX. I connected a wire so that I can connect it to the then. There are some pull-ups. The pull-up is Siwoo that I skipped. Then write enable, read enable, and output enable. So we need to pull down read enable and output enable and have the write enable pulled up. So what this means is we need this guy pulled up, because this means writing to the FTDI has to be disabled. Read enable has to be pulled low to indicate that we want it to spit out the data of itself. And output enable has to be pulled down to indicate that we want it to assert the data pins. This way, on power up, as soon as we start writing data to the FTDI chip, it will start spewing data out onto the data pins. I think that's correct. So let's add labels here. Yeah, we probably will add some prefixes to this stuff to indicate that these are the signals of the FTDI and not collide with FPGA signals. Like basically namespace pollution issue that you would have in software. And OE. Output enable, read enable, write. Write is disabled, so it's high. Okay. What time is it? It's 6. Yeah, we will have to wrap it up soon because it will be dinner time over here soon. So we will just configure this stuff and we will continue building this on the next stream. There's a bunch of more work. I might continue working on the schematic a little bit and push it forward off stream, and then pick it up maybe tomorrow, or I will continue working on this design even if I can't stream next week when I'm in Portland for B-sides. So yeah, but I think you are getting the overall idea where we are going with this design, and that we will basically have an FPGA connected with super speed USB. Thank you very much to Jared and to Dean to helping me find the special chip to connect the two devices together, the FTDI and the USB-C connector, because that's very useful. That saved me a lot of time. And yeah, if you have any more questions or suggestions, please make sure to write that in the comments to this video, or just join in the Esden live on Gitter. So that would be gitter.im Esden /live channel. If you have any suggestions or ideas or better chips or questions where we are going with this, please definitely let me know. The input is always appreciated. And yeah, I hope you have a wonderful weekend and a wonderful Saturday or Sunday, whichever day it is where you are from. And yeah, thank you for watching. And let's see. Oh, wrong. There we go. All right. So thank you for watching. And yeah, join us in the conversations. Thank you very much for all your help during the stream. That is very appreciated. I will put together this will also probably become like a vlog video. That's a pretty good idea that came out of people on Twitter. And yeah, if you have been, thank you for watching.